Haifa, Israel Institute of Technology.
Thank you. First, I would like to thank my collaborators and the committee who invited me to give this talk. So, well, flapping flight is being explored for centuries, maybe, and the last advances in experimental and numerical techniques allow to understand a lot of flow mechanisms. However, most of them are related to insect flight in Reynolds number of few hundreds. In these Reynolds numbers, the flow separates from the leading edge, and because of the span-wise pressure gradient, this vortex drains to the tip and not shed like a two-dimensional separation. Well, this leading edge vortex eliminates the leading edge suction, which characterizes very high Reynolds number flows, in which the lift is mostly perpendicular to the wing direction, while in very low Reynolds numbers, the resultant force is normal to the surface. So high lift is associated with high drag and lower aerodynamic efficiency. There is a great interest in exploring and designing micro-air vehicles, and currently these are they are larger than insects. So basically, we would like to see how these flow patterns change when we increase Reynolds number. And we found a perfect candidate, which is the hummingbird, which operates like an insect. It flaps the wings in the figure 8, but the characteristic Reynolds numbers are much larger, so from few thousands to up to 20,000. So in 20 minutes, it will be hard to explain what's going on over in a hummingbird, but I will try to show the differences between steady wing rotation and flapping wings, and to associate it with different Reynolds numbers, and let's follow that. So in steady rotation, the leading edge vortex, if it's stable, it's fully established. While in a flapping wing, the vortex is born when the wings start to accelerate. And during the wing rotation, in each end of stroke, it sheds away. And a newly born vortex evolves. So basically, it takes time to build the lift and to evolve this leading edge vortex. And this is basically the research was about how fast this leading edge vortex evolves and how it relates to Reynolds number. So this study was done experimentally, and I used the two-dimensional particle image velocimetry, and we complemented these experiments with numerical simulations. So you can see schematically the wing was rotated in a water glycerin solution where I illuminated the flow with a laser sheet, while in the front I had high frame rate camera which captured the images. So here you can see it was a triangular wing with span of 100 millimeters, and the flow was acquired at different span-wise locations, and also it was acquired along the wing center line in order to resolve some of the span-wise velocity which evolves along the wing. Here you can see the schematic description of the shaft and the angle of attack, of course, the geometric angle of attack. Okay, so the acceleration was exponentially as follows, and in order to simulate a flapping wing, it was subject to a constraint, a kinematic constraint, that the wing evolved to 99% of the ultimate velocity when it reached 90 degrees of rotation. So the field of view in these experiments were 60 by 60 millimeters, and I used 1 megapixel camera. And because of the high seeding particles, the high density, I could resolve a vector out from a window of 20 by 20 pixels. These windows were overlapped 50%, so basically the spatial resolution was 0.6 millimeters. In order to obtain high signal-to-noise ratio, each experiment was repeated 20 times, so basically we'll see these averages. Okay, so there are, of course, two frames of references. The wing was rotating, so this is the observer frame of reference, and of course the particles are shed away with the wing in order to fulfill the no-slip conditions. But I will present the results in the wing frame of reference where you can see the no-slip condition. Okay? So I will present everything in a non-dimensional fashion, and I'm using the mean aerodynamic chord, which was 25 millimeters. The location along the span will be normalized by the wingspan, of course. and the instantaneous velocity will be the velocity, the dimensional one, referred to the exact circumferential velocity in each span location. The Reynolds number is based on the ultimate wingtip velocity multiplied by the mean aerodynamic chord and divided by the viscosity, which was 4 times higher than that of water. And in order to identify the leading edge vortex, I splitted the velocity gradient tensor into the symmetric and non-symmetric, and using the ratio, I could identify the vertical regions. Okay, so let's start. You can see here some synthesized straight lines and different Reynolds numbers, starting from very low Reynolds numbers up to Reynolds number of 2000. And in all these images, the wing is moving from left to right, where this bright region is, of course, the illumination reflection line. So you can see that in very low Reynolds numbers, the leading edge vortex is very long. And as we increase Reynolds number, it gets smaller and smaller and more attached to the wing. While when we get to Reynolds number of 2000, you can see 2 vortices, reflecting the fact that this leading edge vortex becomes unstable. Let's look at the evolution. I mean, this is a quantification of the evolution of the vorticity. So you can see here the wing is at angle of attack of 30 degrees. It's the lowest Reynolds number, and it's 60% along the span. So it starts, and I'm starting to show from the very early stages along the wing rotation, just after 10 degrees of rotation, where you can see the leading edge vortex evolves, and this is a somewhat diffused starting vortex. And when we get along the trajectory, the leading edge vortex evolves and reaches steady state at approximately 45 degrees. And later it stays stable. Well, let's look how it looks in Reynolds number of 1000, and this was the last Reynolds number where this vortex was stable, because as you can see, in Reynolds number 2000, it was unstable. So you can see that the vorticity concentration is much higher, and the starting vortex, now it's focused and already shed away from the wing. But now look at this leading edge vortex, and maybe we shouldn't call it any longer a leading edge vortex because it covers about 75% of the chord. And also you can see that the maximal vorticity is near the reattachment point and not near the leading edge. So basically, look, this high vorticity induces reverse velocity, which is very high, and basically you can see here a shear layer evolves. You need to remember this is a 3-dimensional shear layer because the spanwise velocity drains the vorticity towards the tip. And this is how it looks in steady rotation. So basically it evolved and it stopped the evolution, of course, in steady rotation. So the very good comparisons between the experiments here and the simulations allowed us to complement these experiments with the numerical results, which had, of course, the spanwise velocity evolution. So I will show you now the spanwise velocity evolution, which is colored as follows. So these are at Reynolds number 500, at exactly half span of the wing. So when we start this motion, the spanwise velocity is quite low, but it accelerates and reaches values which are comparable to the circumferential velocity. So basically, you can see it's highly 3-dimensional flow field, and it reaches even higher values when we reach 90 degrees of motion. Let's see how it differs in different spanwise locations. So this is near the root, and here we go along towards the wing tip, and we see that the highest values of spanwise velocity is near the root, and it decays when we go along to the wing tip. Also, you can see that these maximal velocities are not in the leading edge, are not in the vicinity of the leading edge. So basically, many studies talked about the fact that the spanwise velocity stabilizes this leading edge vortex, and these results show that it's not necessarily the issue. Maybe the low Reynolds number contributes another stabilizing factor, and it's not only about the spanwise velocity. Let's look and see how it explains the evolution of circulation, and this is the entire circulation in the leading edge vortex. And I will show a non-dimensional evolution. So basically, I took the instantaneous circulation and I normalize it by the circulation that was calculated during steady rotation with constant angular velocity. And these are plotted for different spanwise locations. So you can see that the growth is very rapid at the beginning of the motion, and now we understand why, because the low spanwise velocity do not convex the vorticity towards the wingtip, while after this spanwise velocity is much higher, so basically the growth decays. Also, it explains why near the tip the vorticity accumulates much further. You can see it here, and this is because the highest spanwise velocity are near the root. So basically, the circulation do not grow near the wing root compared to what happens near the wing tip. Okay, but most interestingly, let's look at Reynolds number effect. So you can see here in the lowest Reynolds number, the circulation grows and exceeds the steady state values because this is larger than 1, and this can be a benefit when we try to design flapping wings. Of course, we need to take into account that in the early phases of the motion, the circulation is low, but this will be complemented by the wing rotation at each wing stroke. So it's a multi-parameter study, but look here, there is some aerodynamic benefits. But very interestingly, in high Reynolds number, the circulation growth is very low, which shows and proves that if we try to analyze flapping wings, we cannot do it with steady rotation analysis because the circulation is much lower than that can be a benefit or analyzed when we do a steady rotation. So other studies talk about the fact that the evolution of spanwise velocity can be an analog to the boundary layer which evolves over a disk. And in this analysis, the spanwise velocity is Reynolds number independent, but as you will see here, it is. And look, this is the evolution of the spanwise velocity. These are contours of spanwise velocity, and of course, this is the wing tip, and the wing is going into the board here, escaping from you. So you can see that in the early phases of the movement, the tip vortex evolves, and the spanwise velocity do not evolve yet. But look here, at 45 degrees, look at the difference between what happens in Reynolds number of 1,000 compared to what happens in the very low Reynolds number. So basically, it explains how these results are Reynolds dependent, and it's not about this analogy to the disk theory. And this is how it looks at the mid-stroke. If I try to show and explain the comparison of the total velocity field, you can see here again the comparison between the low Reynolds number and the higher one. Look at the boundary layer; it's much thicker here than what develops on the high Reynolds number. Okay, so basically my explanation is that in the high Reynolds number case, the suction is much higher. So basically, as you go along the span, you have a greater pressure gradient, and this caused the evolution of the spanwise velocity and not necessarily the explanation of the boundary layer over a disk. So I couldn't finish without showing you some raw images, and this is at 50 degrees at the mid-span where the Reynolds number causes a leading edge vortex which is unstable. And look at this, and you can see here a huge vortex evolves and a dead water zone between the shear layer here and what follows the wing. And this is the PIV processing of this scenario. And one instant I will show you at 45 degrees, showing here again the shear layer and the big vorticity concentration. And just in 90 degrees, so slightly further out in the motion, you can see here that this shear layer breaks and it's unstable. It also reflects the fact that during flapping flight, you don't really necessarily need to keep this leading edge vortex continuously above the wing, and you need to keep this vortex only during one stroke. So basically, you can have an unstable leading edge vortex and still benefit from high lift, because you need to keep it only for one stroke. It will shed away during the wing rotation, and a new one will build up later. So basically, the the requirement to keep this leading edge vortex is much weaker than in steady rotation. So in order to conclude, we've seen that the leading edge vortex varies and the size varies in different Reynolds numbers. The span-wise velocity might be not necessarily the only factor that governs the stability of the leading edge vortex. And we also need to remember that the vortex itself is three-dimensional, but if we follow particles along this spiral vortex and consider the shear in these locations, maybe we can follow and get to a conclusion where this leading edge vortex will burst. Also, we saw that in very low Reynolds number, a stable leading edge vortex could give us benefits where we reach higher circulation than in steady rotation, while in the high Reynolds numbers, the steady revolution analysis might be overestimating the current lift that we can reach during flapping flight. So basically, it's very important to do analysis of flapping wings in high Reynolds number on really flapping wings and not necessarily rotating ones. Thank you.
I want to ask about the high Reynolds number, 2000 N. You stated that the leading edge vortex was unstable. You showed us evidence that the vortex structure was complex and time dependent. That doesn't seem to me to be exactly the same as unstable. Can you expand on the instability you're thinking of, or is it just a complex but deterministic process?
Well, it seems to be deterministic, but when I say stable, I mean it doesn't really stick to the leading edge. Okay, so...
Okay. But then it's repeatable. If you do the experiment again, you get the same structure again.
Yes.
Okay,
yes.
I understand. Thank you.
Yeah, and well, one further application of the same type of flow exactly is what is used in sculling, both in synchronized swimming, well, it's not for boy bass, but in water polo sculling is the same type of quick oscillating, and there things to be learned by quick vortex shedding, and you actually say improve a lift by certain combinations of say quick vortex shedding from the movements of the hand. So I can show you some 10,000 or much higher Reynolds number experiments in swimming pool, and well, it's not so clear the vorticity, the balance, but there is a say higher vorticity change of sign, which improves really the lift. So it's an interesting application, not just for the birds, but for swimmers.
I wanted to clarify, you started the wing at a fixed angle of attack from rest. What about the twist before the previous stroke? That's going to produce a vortex as well.
Yes, yeah.
And that would that augment the...
Yes, yes it is. Yeah. It was in very low Reynolds numbers, it actually interacts.
Yes.
I mean, it interacts with the last vortex that were created. But in higher Reynolds numbers, I didn't show it here, it creates a jet, basically.
Yeah, that's what I was...
Because this vortex is really far down, and it doesn't interact, but it creates a jet that augments the image. Yeah.
Just a comment. The number E, the capital E you use in analysis is called Truesdale vorticity number.
Truesdale?
Truesdale vorticity number.
Thank you.
But not very easy. There's a paper. Yes.
Thank you for this. Thanks a lot. Some more questions? Well, just a comment, because I enjoy your point that you know, this problem, as far as I know, and please correct me, so Untitled play a key role in, I mean, getting interest in this flapping wing because of Weisfog, who was a professor here in Cambridge, and we were studying this very tiny wasp, about 1 millimeter, that's Dimitri, who is actually co-author also of this talk, has been studying, and as everyone knows, Thurlighty was a very good swimmer. So I think that gave him also a lot of intuition about what was going on. This is kind of...
Well, he used to act the little Encarsia formosa, which is about
swimming
half a millimeter in size. So there was a slight difference of Reynolds number.
And he couldn't hover.
Thank you.